Hey everybody, hope you're doing well. This is just a quick review of 2019 AP Chemistry FRQ question number 3. Good question. It's got a lot of range of questions that we'll see, and I wouldn't be surprised to see a question like this on this year's test. You can see how these things work. First of all, notice what's going on. You're given a 50 milliliter solution of sodium carbonate, Na2CO3, but you don't know its concentration. So to determine the concentration, the student mixes it with calcium nitrate, 1 molar, and a precipitate forms, and you can see the chemical reaction below. So let's go through and talk about one way to figure out the concentration. Question A says, write the net ionic equation. Just pay attention to what's aqueous and what's solid. If we look right here, we can see that we would have 2 Na pluses and a CO3 minus 2, a Ca plus 2, and an NO3 minus 1, and there's 2 of those. Hey, the sodium and the nitrate are aqueous, so that means the sodium and the nitrate stay in solution. What's left over? Well, your net ionic equation. Your net ionic equation would be the calcium plus 2 plus the CO3 minus 2, and it would form the solid CaCO3. These obviously are aqueous. That's how you do question 1. I bet you that's a 1-point question. Question B. Imagine what's in the beaker, right? We want to look at what's in the beaker. And so we want to draw what's in the beaker. And let's pay attention to what we see there. We see inside of there, and look at the balanced chemical equation. The balanced chemical equation says there's 2 NaNO3. So I see an NaNO3. I see a NaNO3, and I see some nitrates left over, and 2 nitrates left over. Where would those 2 nitrates come from? They must have come from a calcium nitrate that, well, wasn't the limiting reactant, right? Because we know that this was added in excess. This was the limiting reactant. So there must be some excess calcium. The 2 nitrates would probably signify that there's probably 1 calcium ion excess. That would be the simple way to do it, just so that you keep the ratios to calcium and nitrates. Let's look at question number. Let's continue with this question. This is gravimetric. This is Unit 1 stuff, right? And in Unit 1, we're going to be talking about, moles and mole ratios and things like that. And we're going to use that information to try and figure out, molarity and stuff. Let's look at question C. We know that we added 50 milliliters to this and added 100 milliliters of this. That dry calcium carbonate at the end weighed 0.93 grams. Determine the number of moles of sodium carbonate in the original 50 milliliter solution. Let's figure that out from this. Remember the chemical equation, and if you'd have to, you'd write it down. But in that chemical equation, Na2CO3 plus CaNO3 2 gives us the CaCO3 plus the 2NaNO3, the sodium nitrate. So we know that this weighs 0.93 grams, and what we want to do is figure out how many moles of this. So we take the 0.93 grams of CaCO3. We know that there's 100.1 grams in 1 mole. We were given that information right up here. And we know for every 1 mole of CaCO3, there's 1 mole of Na2CO3. We'd be able to figure out that there'd be 0.0093 moles of that. So you want to be able to be comfortable with those types of calculations. I'm pretty confident we'll see something like that on the national exam. The student realizes that the precipitate was not completely dry, claims a result that the molarity would be too low. Do you agree or disagree? Let's see. If this thing was wet, this mass would go up, right? Because there would be calcium carbonate and some water in there, and that would make the mass go up. So if this mass went up, what would we figure out about the number of moles? We figure out that the number of moles would go up because everything is directly related. Well, if the number of moles goes up, that means the molarity would go up. And that can't be correct. So I would disagree. For D, I would disagree. And I would explain the fact that the wet calcium carbonate would increase the number of moles of sodium carbonate, and if there's more moles of sodium carbonate, molarity would have to go up. Let's talk about E. After the precipitate forms and is filtered, the liquid that passed through the filter is tested to see if it can conduct electricity. What would be observed? So we're talking about this liquid right here, because after we went through a filter, this would be in the filter, this liquid would be floating around. Hey, does that liquid conduct? Let's see. I would say for sure, yes, it's conductive. And the idea, of course, is that it contains all those ions. Anything that has a charge that's able to move, so the sodium ion, the calcium ion, the nitrate ion, all of those are present, able to move. And so that's what would be observed. And I would explain it with the ideas of mobile ions. Then we get to this equilibrium problem. And you're going to probably have an equilibrium problem, so I would certainly be reviewing that information. And notice that this is basically sodium carbonate is a basic salt. When sodium carbonate goes into water, the carbonate ion acts like a base. And what it does is it takes away, this acts like an acid, and it turns into this ion and produces this. This is a basic salt because the pH will be greater than 7 when that's present. So the Kb for that is obviously reactants over products. And notice it's a very small number, 2.1 times 10 to the negative 4th. The student decides to first determine the OH of the solution, then use the result to calculate the initial concentration. This is going to be a mathy way of doing what we just did, but it's possible. In question 1, F1, it says identify a laboratory method that the student could use to determine the OH of the solution. Well, you would use a pH meter, because from that you would get the pH. And from that, 14 minus the pH, you could get the pOH. And once you get the pOH, you can go 10 to the negative pOH and get the concentration of the OH minus. So a pH meter would do it for you. You just got to remember the pH square in that calculation. Explain how the student could use the measured value in part F1 to calculate the initial concentration of CO3 minus. Don't do any numerical calculations. So we need you to show some mathematical reasoning here. In that mathematical reasoning, we want to jump in and think about what would the concentration of this be before equilibrium. We know something about it at equilibrium because it falls into this expression, and we know these pieces of information, but we got to know it before. That's going to require an icebox. And so if we have CO3 minus 2, and we'll ignore the water because it's not going to change, we get HCO3 minus 1 and OH minus 1. Let's go through and think about what that icebox would be. Here would be our initial concentration. These would start at 0. That would be initially. There'd be a change. We know that these are going to go up, and this is going to go down. And what value do they go up by? They'll go up by x. So at equilibrium, we'll have x, x, and this is going to go down by x. We'll have that initial concentration minus x. Now, at equilibrium, we know this number. We just could have calculated that in the first one with the pH meter. But if we take these values right here and substitute them into our expression for Kb, and we would have that the 2.1 times 10 to the negative 4th equals x times x. That's the HCO3 and the OH, HCO3 and OH, divided by Ci minus x, Ci minus x. And we would be able to solve for Ci here. The Ci, it would equal basically x squared over 2.1 times 10 to the negative 4th plus x. And we kind of know the value of x if we had that meter, so we could find it that way. Kind of a complex. You basically would only get probably 2 points on that problem. I can certainly see you not wanting to do that problem or coming back to that problem. Looking at G, it says the original sodium carbonate solutions at equilibrium. Is the concentration of the HCO3 greater than or less than the unequal concentration of the CO3 to minus 2? Justify your answer. So it's basically saying in this solution at equilibrium, which we have this expression for right here, in that solution at equilibrium, is the concentration of this greater than the concentration of that? Is the concentration of this greater than the concentration of that? And I would say no way. Look at this number. This number is 2.1 times 10 to the negative fourth. That means you have less reactants and less products and more reactants. And so I pretty much say no way on that one. I would say it's going to be less than. This will be less than this. And I would say in justification, I would use this expression and just say because that's less 10 times 10 to the negative fourth, the value for this would probably have to be less than the value for that. Finally, it talks about H. The student needs to make a CO3 HCO buffer. This is that Henderson-Hasselbalch, that idea of making a buffer with a set point. And they want that set point to be at a pH of about 6. And let's think about this. We know that the Kb is going to be 2.1 times 10 to the negative 4. So pKb is going to be approximately 4. Well, pKa would then have to be approximately 10, right? I'm just guessing here. 10 and 4, so if the pKa of 10 is really way off than a pKa of 6. If you want to make a buffer, the big idea is that in a buffer solution, you want that pKa to be really close to your set point or wherever you want that pH solution to be. Then you can vary concentrations to tweak it a little bit, but the idea is that you want that to happen. So I would say no, it would not. And I would use the concept of the pKa being approximately 10, and of course that one being too far away. Hey, I hope you had a chance to go over these problems, and I hope that you're doing well. Let me finish up by just saying we got 2 weeks left. Next week we'll start talking a lot more about the test. We'll get some stuff from AP Central. I hope that you are willing to gear up your studies, and I hope this is working for you. Take care, and I'll see you around.